Hey everyone, welcome to this explainer. Today we are moving way beyond those basic beginner-level setups to truly master scikit-learn's random forest. We're going to pop the hood on one of machine learning's most popular algorithms and give you a real practitioner's playbook for optimizing it. Okay, let's dive right into this. It's incredibly tempting to just import a random forest, fit it to your data, and celebrate the seemingly awesome results. But I really have to challenge this reliance on out-of-the-box models. Are you leaving critical accuracy on the table just by trusting those default settings? Well, the short answer is almost certainly. Here is our roadmap for today. We'll start with Section 1, Beyond Default Random Forests, then we'll hit Section 2, Tuning Trees and Features, moving to Section 3, Enter Scikit-learn's Grid Search Fee. Section 4 will be our step-by-step optimization guide, and we'll wrap up with Section 5, Real-World Model Impact. All right, kicking things off with Section 1, Beyond Default Random Forests, and what we call the default settings trap. Now, the random forest algorithm is, quite frankly, brilliant. If we trace it back to Leo Brayman's foundational 2001 paper, the theoretical origins are just incredibly robust. By using bootstrap sampling, which is basically drawing random subsets of your data with replacement, and then building multiple decision trees, the algorithm averages out predictions to reduce variance. It works beautifully right out of the gate, and that's exactly why it's so popular. But that convenience, it's kind of a double-edged sword. Because it works so well initially, a lot of practitioners just never touch the control board. And in scikit-learn, sticking with default values often means your decision trees are going to grow fully unpruned. Basically, every single node keeps splitting until the leaves are pure. This risks massive memory consumption, incredibly slow prediction times, and worst of all, severe overfitting if your dataset has a lot of noise. Leaving those dials untouched can seriously hurt your model's ability to actually generalize to new data. Let's move to Section 2. Tuning trees and features. Let's look at the heavy hitters of optimization. So our first heavy hitter is n-estimators. This parameter is pretty straightforward. It simply specifies the total number of decision trees grown in your random forest. Generally speaking, adding more trees reduces the variance of your model. A higher number of estimators gives you a much more stable, reliable prediction, simply by averaging out more independent results. Our second heavy hitter, and this one is absolutely critical, is max features. This controls the maximum number of features the algorithm is actually allowed to look at when it's searching for the best way to split a node. By artificially restricting this number, you force the trees to look at totally different parts of the data. This injects randomness and decorrelates the trees, which stops a few dominant features from just taking over every single tree in your forest. When we map out the theoretical mechanics and trade-offs of these two parameters, it's pretty fascinating. Take n-estimators, for example. A low value gives you fast computation, but really unstable predictions. A high value gives you stable predictions, but, it's computationally slower. But the crucial thing to remember here is that adding more trees does not cause overfitting. Now consider max features. A low value gives you highly decorrelated trees, which is great for preventing overfitting, but it might make the individual trees a bit too weak. A high value, on the other hand, makes the trees highly correlated, meaning they all just start making the exact same mistakes. That brings us to Section 3, Enter Scikit-learn's Grid Search CV. Let's talk about automating the search. Think about how we usually approach this. First, there's manual tuning. You change a parameter, run the model, check the score, and repeat. It's basically guessing and checking, which, let's be honest, usually leads to a lot of lost weekends. It's extremely inefficient and carries a really high risk of bias because you might accidentally just tune your model to memorize the specific test set you're using. But then there's Grid Search TV. This tool is a total game changer. It automates the misery away. You just hand it a grid of parameters and it exhaustively tests every single combination. Even better, it uses built-in cross-validation. That means it splits your training data into multiple folds, trains on some, validates on others, and basically guarantees a systematic, rock-solid result. All right, Section 4, Step-by-Step Optimization Guide. This is your practitioner's playbook in scikit-learn. So what does this actually look like in Python? Well, it's a super clean workflow. Step 1, define the estimator. You just instantiate your random forest classifier. Step 2, create the parameter grid dictionary. This is where you list out the hyperparameters, like our heavy hitters and estimators and max features, along with the specific values you actually want to test. Step 3, instantiate grid CV. You pass it your random forest model, your parameter grid, and define your cross-validation strategy, like save 5-fold CV. And step 4, you fit it to your training data. The algorithm will now run through every single combination, handle all the cross-validation, and hold on to the absolute best performing configuration for you. Now, if you aren't exactly sure where to start for step 2, we've put together a really practical minimal tuning grid cheat sheet you can use right away. Notice our heavy hitters sitting right at the top. For N estimators, testing 100, 500, and 1,000 is a fantastic starting point. For max features, checking the square root of your features, the log base 2, or none, which just uses all features, will definitely cover your bases. We've also included some depth and sample parameters here. Those are super helpful to regularize the trees and prevent that massive memory consumption we warned about earlier. And here is a crucial insider tip straight from the scikit-learn developers themselves, from their official course materials. They state, tuning the n_estimators for random forests generally result in a waste of computer power. We just need to ensure that it is large enough. This is absolutely gold. Don't waste time testing 50 different values for n_estimators. Just set it to a reasonably high number, like 500 or 1,000, and let GridSearchCG spend all its computational energy figuring out the much more sensitive parameters like max features and your tree depths. Finally, let's wrap things up with Section 5, Real-World Model Impact, and look at the actual payoff of all this tuning. To see why this matters, let's look at a specific real-world example from an IBM developer tutorial on credit defaults. They took a dataset of credit card users and built a random forest to predict whether a customer would default on their payments. They ran the default random forest, checked the results, and then ran a grid search CV targeting things like max_depth and min_samples_split. And the result of that tuning process? Using Grid Search Grid boosted the model's accuracy by just over 2%. Now, 2% might not sound like a huge leap at first glance, but in financial risk modeling, where predicting a default incorrectly can literally cost an institution millions of dollars, extracting an extra 2% of predictive power simply by tweaking parameters is an absolutely massive payoff. It's quite literally the difference between an okay model and a highly competitive, production-ready powerhouse. Which leaves us with a pretty important question to ponder. What hidden accuracy is currently locked away inside your default models? Well, you now have the theoretical understanding of the heavy hitters, and you've got the practical Grid Search VD playbook to go find out. I highly encourage you to go apply this to your own scikit-learn projects today and see what you can unlock. Thanks so much for joining me for this explainer, and hey, happy tuning.